The title of this presentation is Solving PDEs with the Matryoshka Neural Operator and Physics-Informed Neural Networks. To begin with the presentation overview, we'll be introducing several different types of methods for solving PDEs. And in doing this, we'll want to focus our attention on introducing neural networks and their counterparts through deep neural networks for training models to approximate PDE solutions from previously unseen data and initial conditions. And in bringing up these topics in our discussion, we'll want to establish some connections with previous works on a quantum algorithm, which allows us to numerically approximate different solutions of PDEs, which can be used as training set data for the neural operators in the physics-informed neural networks. And in doing so, we'll be discussing results from training neural operators for solving PDEs and looking at different ways to compare and contrast these methods and what is the possibility of making use of the neural operator and the neural network approach for being able to recover very similar, if not the exact same types of solutions that we observed and were able to generate with the quantum algorithm and even other related algorithms. So we're going to begin by discussing some references from the literature and some other pieces of information that are around from either conference presentations and other things, which can help give us an idea of what the neural operator perspective is for solving PDEs and how this relates to different parts of or different ways for solving PDEs. And generally speaking, a lot of it relates to the fact that the neural operator can make use of some type of training set data for different solutions from the PDE, which can be generated by finite differencing, classical solvers, or even quantum solvers. And this can allow us to generate additional trajectories for the solutions of other PDEs for other initial conditions without having to hard code anything into the system. And we'll show that we can simulate these networks and make use of neural networks for generating PDE solutions by providing some training set trajectories, which were gathered from a quantum algorithm that I was able to save from the simulations and feed directly into some scripts from a publicly maintained GitHub that's called Neural Operator, that I'll present some further details on the contributors and what parts of the script are useful for training these neural networks. But from the first reference that we saw in MDPI on the left-hand side, we can see that there are some applications of Fourier neural operators and networks for simulating waves as they propagate in fast photoacoustic environments. And this relates to the fact that waves, when they permeate or they propagate through mediums or different types of mediums, can either have accelerated or slowed down motion, which demonstrates how fast the wave oscillates and achieves its maximum and minimum given from the peaks and troughs that are given by menu-sinusoidal wave profiles, which are obtained from different PDE solvers, whether classical or quantum ones. In the middle reference, we can see that also the Matryoshka neural operator has an application to weather and climate models, because these are often relying upon series or systems of PDEs or systems of ODEs, which can try to incorporate different types of constraints for how the weather, how different types of environmental activity is going to be propagated forward in time from some initial estimate of what the weather would be earlier in time. And then we can see in the final reference here that the Matryoshka neural operator also has another way from the same from the same authors, which presented this on climate models. It can also be used for obtaining fast PDE solvers for multi-scale physics, for trying to see different ways that physics on different scales can be studied and tried to be approximated from a PDE solver. And there are also some references on the physics-informed neural networks, and the physics-informed neural networks has a lot of connections and relations to the Matryoshka neural operator and being able to solve PDEs with neural operators, because there are physics-informed neural operators, such as given in this reference, which provides a couple of different applications of how these neural operators can be used depending upon the training set data and the expected performance of these types of networks after we train them to determine how accurate a readout from a PD solution could be. And there's even another application given in the other reference on the right-hand side of the slide that is demonstrating in a similar way to how waves can be studied in photoacoustic medium, how seismic wave propagations and inversion problems can also be studied with neural operators. So these references from these past two slides demonstrate the fact that there are many different types of applications of neural operators and physics-informed neural networks, and they can provide us different perspectives from either the performance of classical or quantum algorithms and being able to generate solutions for neural networks in a completely different manner from not being able to actually code in either a cost function or an optimization routine for obtaining some approximation to the PDE solution, which is used by a lot of quantum PDE solvers and even classical PDE solvers for approximating behaviors and nonlinearities. And now we're going to be mentioning the repository, which is used for the neural operator. So this is the GitHub repository, and it's called the neural operator, and it's from these 4 contributors. And they provide a lot of great overview in terms of how one can try to learn about neural operators in infinite dimensional spaces, as well as establishing connections between graph networks to solve PDEs, and establishing also other connections between the physics-informed neural networks that we had mentioned were already apparent from the connections with neural operators from the references in the previous 2 slides, and how this can all be applied for generating trajectories of PDEs for different types of solutions. So I'll demonstrate the specific cases of the solutions for the PDEs that they have, and then I'm going to also highlight how one can introduce modifications to these scripts and feed in training set data from either finite differencing solving, or in the case, how I used from trajectories from a quantum algorithm that I had lying around from a previous project, and how one can look at the performance of the neural network and that it's actually able to exactly approximate other types of trajectories for solutions to the PDEs, even though it didn't have any a priori information about the initial conditions of these PDEs or the time step that the PDE would take, and so on and so forth, and how the neural operator is a very powerful method for just being able to have a type of black box implementation for being able to generate other types of PDE solutions with very little information rather than just what's input into the network as the training set data. And so the initialization script that they have in their GitHub, it just says, you just need to run this first to have the prerequisites for actually running their code for training the Navier-Stokes and the Darcy flow, which are the 2 examples that I'll just be providing an overview of, and how this relates to nonlinearities that I was able to observe for many different types of PDEs, whether they relate to Navier-Stokes, Kamasa-Holm, Hunter-Saxton equation, or the Maxwell equations, which relate to different ways in which nonlinearities from magnetism, electricity, or electromagnetism and gravitation and wave propagation can all be studied together from the perspective of this neural network, or this neural operator, and the physics-informed neural network. So as we had mentioned, the scripts for the training procedure as given by these 2 scripts are given in the repository, and you can pretty much take it out of the box, attempt to change the training set data that's fed into the physics-informed or the neural network or the neural operator, and be able to obtain some type of readout for the solution from the nonlinearities that are previously available in the training set data that's fed into the neural network. So this is demonstrating a very easily in a very, or I don't know, easy, but, a very readable way and powerful way in which the neural network can be used to solve PDEs, and how this relates to properties in the architecture of physics-informed neural networks and even deep neural networks, which can be used for classifiers for other types of problems, whether you want to do other biologically oriented problems that could have some relation to a system of PDEs, which could be viewed as a type of constrained optimization problem. And we're going to be drawing some attention to a 2022 archive preprint that I have on quantum algorithms, which we can use to directly feed training set data to the neural operator for approximating new solution curves to a given PDE. In this archive preprint, I looked at ways to numerically approximate solutions for 15 partial differential equations. And it was primarily under the quantum physics category, because it's making use of a quantum algorithm, which is more or less an extension of the variational quantum argument solver, which is in turn related to a numerical linear algebra problem, which is looking at a way to computationally approximate eigenvalues and eigenvectors from a statement of a partial differential equation initial value problem. And this is given by the fact that even on the first page of the preprint, I have many keywords to draw our attention to the broad scope of this algorithm and its connections to be looked at or to be further explored with neural networks, deep neural networks, and physics-informed neural networks, like the types of connections that I've been discussing in this presentation, through the fact that quantum computation, variational quantum algorithm solver, or variational quantum algorithms and variational quantum eigensolvers and variational quantum computing can generate and provide a simulation method in which training set data can be fed and generated that we're going to be using for these neural networks, and how we can look at the performance of the neural networks on different types of training set and simulation data from a wide variety of optimizers, whether it be, as I've indicated in some of the keywords here, the Nevergrad optimizer, the neighborhood algorithm, the particle swarm optimizer, the competitive particle swarm, sequential least squares SciPy optimizer, or as well as making use of the QSIMCIRC simulator to simulate the wave function of the solution as we propagate forward in time, which all can be used to look at performance and different characteristics of the neural network architecture that we're going to be trying to approximate the solutions to the PDE with the Matryoshka neural operator. And now I'm just going to be demonstrating some of the types of nonlinearities that we observe from a couple of PDEs and how one can use solutions and approximations for the solution for the PDE as training set data for the neural operator directly from the scripts in the GitHub, which I used, or which I mentioned previously from the 4 contributors, and how this allows us to generate very close approximations to other types of solutions for a different class of initial conditions and different time step magnitudes with the neural operator, which highlights the ability and the potential of the neural operator to be applied to many other types of nonlinear problems. In the case of the Hunter-Saxon PDE, we can see that I have this statement of all of the partial differential equations in the preprint itself, which, just to make the presentation a little lighter, I haven't included. But we can see that we can run a numerical experiment for the quantum algorithm, which would constitute training set data for the neural operator by running the quantum algorithm through a time evolution procedure for, in this case, 500 steps, or however many hundreds or thousands of steps. In some case, I ran almost 20,000 time steps of evolution for another PDE. But in this case, for the Hunter-Saxon PDE, we can see that there are many different types of nonlinearities that are present in this PDE. And we can look at performing or obtaining or performing optimization steps with different time step magnitudes and different types of initial conditions, in which sometimes the quantum algorithm, which we're using to approximate solutions of this PDE with, it can demonstrate a lot of highly non-trivial nonlinearities before stabilizing out to some sinusoidal type of profile for the solution. And we can also see that, as given in the second plot, there's a blue line which has fluctuations from the sinusoid that are very much smaller in comparison to the other curve that's on the same plot, namely the second plot, which can demonstrate the sensitivity of our quantum algorithm to different initial conditions, as well as different time step magnitudes, which can impact the overall profile of the solution that our algorithm is approximating and generating. And similarly, for other types of simulation results, we can zoom into a more narrow profile of motion for the Hunter-Saxon PDE from just 100 time steps instead of for 500 time steps. And we can see that if we take the optimizer time step to be very small, namely like 1 times 10 to the minus 3 in comparison to optimizer time step for 1.2, which is given in the first plot in the top, we can observe that there can be differences in the amplitude of fluctuation in the amplitude of the sinusoidal profile for the solution for the 100 time steps of evolution, depending upon the initial conditions and the time step of the optimizer, which we had mentioned of we could observe for different types of sinusoidal profiles that we obtained for the Hunter-Saxon PDE when we ran the time evolution for 500 time steps. And we can observe different types of similar behaviors for the quantum algorithm in the remaining 3 plots. If we look at the Komatsu home PDE, I've demonstrated some types of properties of this third order partial differential equation in some other seminar presentations and other presentations on the channel. But we can observe that for this class of solutions, for some class of initial conditions, the readout that we obtain from the PDE and the measurements that we extract, it can be almost like a linear function, which can decrease with respect to the time step number. So this generates, and this constitutes another set of training data that we can feed into the neural operator for being able to approximate a linear function that's strictly decreasing with respect to the total time step with respect to the total number of time steps of the time evolution that we're running. And for another PDE, the Lin-Hsien PDE, we can generate different types of plots to compare how the ansatz performance or the initial condition that we feed into the PDE can differ depending upon what time step magnitude. And again, if we vary the initial condition broadly or significantly. If we try to introduce widely different initial conditions at the beginning of the time evolution for this PDE that we're trying to solve, namely the Lin-Hsien PDE, we can observe that there can be certain time points of the evolution where one magnitude of the solution approximation is a lot larger than another magnitude, which then would decrease or change with respect to the time evolution, as we can observe from these three PDE solution plots. For the Maxwell equations, this is known to be a system of partial differential equations that has connections with not only electromagnetism, but also with gravitation in Einstein's equations, which we also had investigated in the 2022 archive preprint from some numerical solutions of Einstein's equations. And in this case, we can see that we're able to recover some very well-known behavior of the properties of the electric and magnetic fields, in the sense that the magnitude or the presence of the electric field with respect to some fixed point of reference decreases like a power law with respect to the distance that we take from the initial condition through the time step. And finally, for the Navier-Stokes equations, we also exhibited the fact that the sinusoidal profiles of motions, which can be used for studying several different properties of fluid dynamics and some type of more simple cases of fluid flow, can also be obtained from the algorithm. And so this is demonstrating across the different types of PDs that we generated data from the quantum algorithm, how different types of training set data can be obtained for the neural operator, which can be used to inform and test future experiments, or even inform our current understanding of the performance of Matryoshka neural operators and physics-informed neural networks for solving partial differential equations. And thanks for watching.